Okay, we're going to look at some more limits here. In this case, we'll look at some rational limits, a greatest integer function limit, and something else, a little bit of a potpourri of limit statements here. But the main focus will be rational functions in the beginning. So we're looking at in 26 and 27 and 28 and a couple other ones, we're just looking at the limit as x approaches infinity. So I'm looking at essentially the end behavior model or end behavior asymptote, remember from your pre-calculus days. So we've kind of already answered these questions in the past, but it's a good review because we're in the limits section here, so let's just talk about these questions again. Easiest way to handle these infinity limits is to consider the end behavior model and asymptote, like I said, and then these answers are pretty straightforward. So if you recall, the end behavior model is the highest degree term. In this case, since we have a rational function, which is a quotient of two polynomials, you take the highest degree term of the numerator and the highest degree term of the denominator, and then you simplify it. So in this case, it would be 2x cubed over x cubed. And since these guys cancel, you're left with 2. So that means that end behavior for very large values of x, how big? Going towards negative and positive infinity, my function values are getting very close to 2. So that means you have a horizontal asymptote at 2. Well, we don't care about that. I mean, it is helpful for your answer, but that's how your function values are going. So that one's all set. Next one again, end behavior model of the numerator. In this case is 3x. 3x. The end behavior model of the denominator is x squared. So if we simplify that, we get 3 over x. So for very, very large values of x, what kind of function values am I getting? Well, if I put a huge number in the denominator, I'm doing 3 divided by a very large number, that gets very close to 0. So therefore, our end behavior asymptote, in this case, would be y equals 0. That means as x goes towards negative infinity and positive infinity, my function values are getting very close to 0. So therefore, both of these limit statements are also 0. 28 doesn't have a horizontal asymptote. It still has an end behavior asymptote. They're both horizontal, but it's an oblique asymptote, if you recall, since the degree of the numerator is higher. Let's just consider the end behavior model again. The end behavior model of this one is x to the 4th over x cubed, which is equal to x. So therefore, I don't know what the end behavior asymptote is. I don't really care. I just know it's going to be something like y equals x plus some constant. And I could determine that by doing long division here, but I'm not really interested in doing that. All I know is that if I plug in very, very large values of x, meaning very large negative and very large positive, what kind of function values am I going to get out of this simplified version of our function? Very large values, namely positive and negative infinity. So that means this goes towards negative infinity, and this goes towards positive infinity. And again, these should be a review of your pre-calculus statements that you did earlier in the year. Last year. So here's, as opposed to looking at infinite limits, we're looking at the function values close to the asymptote. And again, you looked at these last year in pre-calc. Let's just review what are the critical parts of a rational function. Then we'll do a rough sketch of it, and then we'll answer these limit statements here. So the critical pieces are intercepts and asymptotes. So the intercept in this case is you set the numerator equal to 0. You get 0, so that means your x-intercept is 0, 0. Your y-intercept, you let x equals 0. So that means you get 0 over 0 plus 3, which is still 0, which is 0, 0. So therefore, the x and y-intercept are the same, namely the origin. Your vertical asymptote is you set the denominator equal to 0, which in this case is negative 3. And your end behavior model is x over x, which is 1. So we're going to say our end behavior asymptote is y equals 1. So here's a muted rough sketch of our rational function. I don't have a lot of room here. My vertical asymptote is at negative 3, so I sketch negative 3. My horizontal asymptote is at 1, or end behavior asymptote is at 1. And the only other point we have is this one right here at the origin. So since it has to go through the intercept, the easiest way is to start at the intercept and then work your way towards the asymptotes, and then consider the multiplicity. Well, since the multiplicity of the numerator, or the x-intercept in this case, is odd, that means it must cross through the x-axis, the x-intercept. So therefore, it must go through it. It does not touch it, do that little bounce thing, if you remember. So therefore it curves up towards its asymptote. Why? Because functions love their asymptotes, and consequently it goes down over here. Since this has an odd multiplicity of x plus 3, therefore since this is a negative infinity, we want to start up here at positive infinity and come down and go along the horizontal asymptote again. So again, this is a review of pre-calculus, a little crash review on drawing rational functions. So as x approaches negative 3 from the left-hand side, here's negative 3. That's a negative 3 down there, Negative 3 from the left-hand side, my function value is going up towards positive infinity. So we're just going to write infinity. You don't need to say positive infinity. Negative 3 from the right-hand side, my function value is going down. You need to write negative infinity. And this one is just asking what is true about the limit at x approaches negative 3 from the left-hand side and the right-hand side. Well, since these two function values are different, the limit in this case does not exist. On the AP exam, they either give you positive and negative infinity, or they'll say does not exist. These two statements are equivalent, but they won't make you choose. They won't say letter A is positive infinity and letter B is does not exist. They're just going to give you one or the other. And there's not going to be too many questions like this on the exam anyway, so if there's one, you're lucky. Okay, so this is just one with one vertical asymptote. Here we're going to have two vertical asymptotes down here, x squared minus 9. So again, we're just going to go through the critical pieces, the intercepts, the asymptotes, and draw the graph, and then consider the limit statements that are given A through F there. So x-intercept, again, you set the numerator equal to 0. 1 equals 0 doesn't make any sense, so there is no x-intercept. Y-intercept, you let x equals 0, so that means this crosses out. I'm left with negative 1/9. So that's 0, negative 1/9. Vertical asymptote, you let x equals 0. Well, I'm going to rewrite this. You let the denominator equal to 0. I'm going to rewrite this in factored form. And obviously we have two vertical asymptotes at x equals plus or minus 3. Our end behavior model, which will help us with the end behavior asymptote, is 1 over x squared. Y equals 1 over x squared. And for very large values of x, what kind of function value do I get out of this? 0. So my end behavior asymptote is y equals 0. So unlike the previous graph, I'm going to do some different colors because there's a lot more going on in this picture here. So I will choose a different color for the asymptotes. My asymptotes are at plus or minus 3, almost symmetrical. My horizontal asymptote is along the x-axis, y equals 0. And a different color for the function itself. The only critical function value we have is the y-intercept, which is 0, negative 1/9, which is down here. So since there are no x-intercepts in between negative 3 and 3, and you have a y-intercept in between there, you typically want to start your graph there. You have a choice. You can either draw your graph and go up, or you can draw your graph and go down. I can't go up because there's no x-intercept in between 0 and positive 3, so it has to go down. So this goes down like that. Likewise, there's no x-intercept in between these. There's no x-intercept at all, but there's definitely not one in between here and here, so this also has to go down. So you almost have a downward parabola in the middle of your rational function. Since both of these have odd multiplicity on the asymptotes, that means they have to change sign on either side of the vertical asymptote. So over here you have negative going towards negative infinity. That means it must be positive infinity to the right. So it comes down along the vertical asymptote and then goes towards its end behavior asymptote. And the same argument over here, odd multiplicity, so negative here, positive here, and goes towards its end behavior asymptote. So here's a rough sketch of our graph, and then here are some limit statements we want to consider. X approaches negative 3 from the left-hand side. Negative 3 from the left-hand side is going up towards infinity. Negative 3 from the right-hand side, my function value is going down towards negative infinity. As x approaches negative 3, again, the limit values do not agree on the left and right-hand side, so my limit doesn't exist. X approaches 3 from the left-hand side. That's this asymptote here. My function value is going down, so that's negative infinity. A right-hand limit is on this side over here, so that's going towards positive infinity, and likewise, this limit doesn't exist, since the left and right-hand limits at positive 3 do not agree. So I believe that's enough for rational functions. We're now going to look at to determine whether or not